Hello and welcome to our presentation on the design, fabrication, functional testing, and simulation of shear flow over soft substrates by Esteban Espinoza, James Doe, David Sanchez, and Mathew Morano from the Chemical and Biomedical Engineering departments. This project was done for our Microfluidics Fabrication and Design course instructed by Professor John Lee in the spring of 2022, and this project was advised by Dr. Anand Ramasubramanian. The soft substrate in this case is a polyacrylamide gel used to create an environment of certain stiffness for shear flow to be observed upon. Shear flow will be demonstrated using 1% titanium dioxide solution and water. In cell culture, the soft substrate is meant to simulate different organs of the human body and can be used to observe how cells behave and grow on said organs. The objectives of this project are as follows. First, to design and fabricate a microfluidic device that creates flow over a soft substrate. Second, to demonstrate functionality of the device by showing controlled flow over the soft substrate. Lastly, to simulate wall shear stress in a similar size channel to show the relationship between flow rate and wall shear stress and estimate the flow rate necessary to produce physiological wall shear stress values. There are three important principles of operation involved in our microfluidic device, the first of which being the Navier-Stokes equation, which is the fundamental equation describing the flow of incompressible Newtonian fluids. On the left-hand side of this equation, the single terms correspond to the fluid acceleration and convection, representing the inertial forces. The terms on the right-hand side correspond to the pressure gradient and viscous forces. The second principle of operation is shear stress, which has an equation that shows the linear relationship between viscosity and shear rate, with shear rate increasing as velocity increases. As seen in the diagram, shear stress is higher along the edges of a channel as opposed to the center, which is part of what we wish to observe in our device. The final important principle of operation involved in our device is convection diffusion. This equation accounts for both the active mass transport or convection due to the fluid flow and the diffusion within the solution. The first term on the right-hand side of the equation corresponds to diffusion, while the second term corresponds to convection. Here are two published devices that operate similarly to ours. The schematic on the left shows a PDMS microchannel assembly to create flow over a polyacrylamide gel, while the one on the right shows the gel molded by a cavity created using an SU8 photoresist and two glass or metal walls. The materials used for the polyacrylamide gel include 700 microliters of sterile water, 200 microliters of 40% acrylamide, 100 microliters of 2% bisacrylamide, 1 microliter of tetramethylethylene diamine, and 10 microliters of 10% ammonium persulfate. This gel solution is then pipetted into the channels on a silanized glass slide. The gel is left to cure for about 15 minutes with a cover slip on top that has been pre-treated with 150 microliters of Sigma coat, which is meant to reduce the cover slip's adhesiveness to the gel. To the right can be seen the polyacrylamide gel mid-cure using our initial dual-channel design.
Device design. Materials used for the device. Acrylic for the top piece was used with 70 millimeter in length, 1.5 millimeter holes, 60 millimeter by 10 millimeter spacing. 3M9629 tape was with the thickness of 100 micron and 60 micron backing layer was used for the bonding layer and stencil layer. 3 layers of tape without backing layer for the bonding layer, 60 millimeters in length, and 1 layer for the stencil layer, 60 millimeter in length. Silanized glass slides of 70 millimeter in length used for the bottom. Some key dimensions from the 2D cross-section view. The gel is shaped with a stencil layer, which includes the backing layer, that comes out to 160 micron. The bonding layer is 3 layers of tape without the backing layer, which comes out to 300 micron. The clearance for the channel is 140 micron. Fabrication process. First step, cut the stencil and bonding frame. The glass slide or acrylic is used according to which piece of the device is made, and the tape is laid accordingly. The second step, gel is cured within the constraints of the stencil with the backing layer on. Third step, remove the backing layer from both pieces for the top and prep gel slide. The fourth step, align the two pieces and press to make the device. Fabrication equipment. The laser cutter was used to cut the channels for the bonding layer and stencil layer. Engraved lab software was used to achieve this. Some of the cutting parameters are the stencil layer was cut at 85% power and 20% speed. The bonding layer was cut at 80% power and 10% speed, which allowed for ease of removal of the cut channel pieces. Acrylic tops were cut with 100% power and 0.4% speed. Some fabrication results. The first image shows the bonding layer on top and the stencil layer cut out on the bottom. The second image shows a fully built device with the fluid interface connectors taped on with tape gaskets.
Experiment plan. Our overall experiment was to compare the time it took for titanium dioxide particle to be flushed from inlet to outlet over a polyacrylamide gel in a glass slide using water. First, we flowed titanium dioxide at 200 microliters per minute. Then we flushed both devices with water at 1000 microliters per minute, and our overall operation conditions were same room temperature, equal level, and overall same system. As you see in the right image, we have our titanium dioxide inlet, and our outlet is our syringe pump. The overall experimental apparatus was simple. As shown in the first image to the left, our inlet was connected to a tube that had titanium dioxide or water. Then it was connected to a tube that was linked to our microfluidics device that had an interface connector with the tape gaskets around it. And then the outlet had the same interface connectors with the tape gasket with the tube connected to our pump syringe. As shown to your right image is just a close-up of the microfluidics device connected to our tubes and interface connectors. We took our videos using our phone because it was much simpler to see the actual particles flowing through one end to another. And then at the end, our results, we took pictures of our outflows with gel and without the gel using water. Here is a functional demonstration of our device. It's displaying titanium dioxide flowing over polyacrylamide gel from inlet to outlet at 1000 microliters per minute. Our experiment resulted in these two images. On the left side, we have titanium dioxide post-wash without gel, which resulted in discharge time of 5.25 seconds. On the right side, we have titanium dioxide post-wash with gel resulted in a discharge time of 7.8 seconds. We got this results by comparing a particle from each of the devices and seeing how fast it traveled from inlet to outlet. And again, we got these images from a microscope device.
As mentioned, the significance of this project is that it is intended for cell culture. Wall shear stress is the stress on channel walls due to fluid flow and is important for replicating physiological conditions in cell culture, as shown on the right. For the simulation, Objective 1 was to plot wall shear stress as a function of flow rate in COMSOL, and Objective 2 was to estimate the flow rate necessary to produce an average wall shear stress that is similar to what's observed in vivo for endothelial cell culture, using the equation on the left. These were the parameters for the COMSOL simulation, and the viscosity and density values were based on what has been used in endothelial cell growth medium for cell culture experiments. A no-slip boundary condition was also necessary to estimate wall shear stress, and a mesh of normal element size was used, as shown on the right. The geometry was similar to our microfluidic ship, and to estimate wall shear stress, shear rate times viscosity was used. For simulation Objective 1, these were the plots that were generated representing the channel cross-section. And in the first figure, there's a flow rate of 50 milliliters per minute, which yielded a maximum wall shear stress of about 5.6 times 10 to the negative 4 nines per centimeter squared. In the second figure, flow rate was doubled, and as a result, the maximum wall shear stress was doubled in comparison to the first figure. This shows that maximum wall shear stress and flow rate are directly proportional. To summarize the project, a microfluidic device for creating flow over a polyacrylamide gel was designed and fabricated. To fabricate the device, laser cut acrylic and laminate was placed over the polyacrylamide gel and glass slide to create a microchannel. Functionality was shown by flowing aqueous titanium dioxide over the gel using a syringe pump. An experiment showed that the inclusion of a gel slows down particle movement in the chip. And lastly, simulation showed that shear stress increases linearly with flow rate, and that wall shear stress can be estimated using an equation that is dependent on the following variables. We would like to thank Dr. John Lee for guiding us through all stages of the project. We'd like to thank Dr. Anand Ramasubramanian for his consulting guidance. Thank you to Joshua Tran for helping us out with fabrication and laser cutting. And we'd like to thank Dr. Alfred Ronaldo for guiding us in the MPL.